Hey guys, today we're going to be talking about graphing and a little bit about graphing analysis and what we're going to be looking for this year. We'll start with just talking about some basics related to creating your graphs. We're going to be creating tons of graphs this year, and so it's important that we do so in an appropriate manner. And so just the basics. Obviously, we're going to want to create our X and Y axes first and make sure that we label them. Labels are critical. They inform the reader of what they're looking at. They let me know, they let you know, they let somebody else looking at your graph know what your variables are. And for the most part, our independent variable should be on the x-axis, which means our dependent variable is going to go on the y. There'll be a couple instances this year where we might graph the dependent variable on the x just because of the way that particular experiment goes. But in 95% of the cases, we're going to be graphing our independent variable on the x-axis. And we'll talk about those other few instances specifically as we get to them. So independent on the x, dependent on the y. We have labels as to what those variables are, and in the label we should also include units. Okay, so the label for a given axis is the name of the variable. Oftentimes we'll also put the uncertainty, and then every time we should have the units for that particular variable. Once you've drawn and labeled your axes, you need to determine what interval you're going to use. Make sure that it's appropriate. When creating graphs, you want to make the most of the space that you have. If you have a piece of graph paper, you need to think ahead a little bit so that the graph fills up the most amount of space possible, but it actually all still fits on your paper. You don't want your graph crammed into the bottom left. You don't want it to run off of the page, and you need extra paper just to see it. So when we create graphs by hand, you have to think it out a little bit more. When we use Logger Pro to create our graphs, it's a little bit easier because we can manipulate those axes as we go so that they're the most appropriate size, but also making sure that you're using the right units as well. As we mentioned here, if we're measuring plant growth, which we will not do this year, but maybe in biology we're measuring plant growth each week, you wouldn't want to use meters as your units because that would be way too small. That would be an inappropriate unit of measure. You'd be using millimeters or perhaps centimeters if it was a particularly fast-growing plant. So keep that in mind. And then down on this graph, we see that they actually don't start at 0. Anytime that we really want to see that 0, 0. So we want the origin visible on our graph. If it's impractical, then we can adjust where the axis starts. But ideally, we want the origin. We should never do this, though, and this is something maybe you did in previous classes, this little like graph break thing where you can go from 0 to like 600 in a magical instant, and then 700 and then 800. We're not going to do that. That doesn't work this year. Okay, we want the scale of our graph to be appropriate and the increments to be consistent, which doesn't happen with that. Then we're going to give it a title. All graphs should have titles. All tables should have titles. All right. All graphs and tables. And typically, especially if you're putting together some type of formal report, you might say graph 1, and then its title, and then you might have a second graph and graph 2 and its title, and this allows you to reference back to them a little bit more easily. You can talk about what you're looking at in graph 1 and graph 2 instead of having to write out the entire title. And the same thing goes for our tables as well, table 1, table 2, etc. The typical format for a title is the effect of whatever's on the x-axis, because that is typically our independent variable, on y, which is our dependent variable. Or if you're just going to say one versus the other, time versus speed, for instance, in that case, the y variable comes first, the x variable comes second. It doesn't particularly matter to me which format you use, as long as you are consistent and accurate. Then we're going to plot our data points. Depending on the experiment, you might be collecting uncertainty data, and in that case, you're also going to add error bars. We won't do that every time, but we will throughout the year occasionally. And then once we have our data, we're going to want to try to determine the relationship. The whole point of creating a graph is to visually determine the relationship between two sets of variables. And so we want to put some type of fit line in there, whether it's a linear fit or a curve fit. But we're not going to just connect the dots. If I have a graph, let's do this. If I have a graph, y versus x, and I have a data point here, and a data point here, and a data point here, and a data point here, doing this right here doesn't really, that looks like a heating curve actually, a phase change graph. That doesn't really do anything for me. We want to add a fit line, which might look something more like that. So don't connect the dots, add fit lines, add what we call trend lines. It may be a curve, it might be straight, depending on what type of relationship it happens to be. Because that's really what we're looking at. We're trying to build models, we're trying to build mathematical models of relationships between variables, and using our data to determine what those relationships are. So now, some things to look out for in the actual set of notes, if you have that pulled up, or if you're looking at it. This fantastic picture here is actually a link to a page that talks about graphing, and I would take a look at it. It's a good reference. It gives you some really good examples of bad graphs on the internet, and it's a good discussion about critical thinking and looking at data, and how easy it is to manipulate graphs to show what you want, and that the way you present a graph can be misleading, and it might not be intentional. But when we're talking about things on the internet, the reality is a lot of times graphs are presented in a way to be intentionally misleading, and there's a couple really good examples on this site that are worth taking a look at. So I would encourage you to go to click on the link, take a look at it, take a look at some of those references. But the thing that I really want to focus on from that website is this piece here. So we have some red flags to look for when graphing. Not just when you're reading other graphs, but also when you're making your own. We already mentioned the clear axis labels. Make sure your labels are axes. Truncating or adjusting the axes so that it's unclear or that you don't notice where it starts. There's a couple good examples of that on the website. Not including all the data, which if you're doing something like a pie chart is going to make it so that it doesn't all add up to 100. Leaving information out. This is more for that intentional representation and misleading, but using straight up deception. This, I think, is important for us. Pick the appropriate type of graph. When you have two quantitative variables, okay, two quantitative variables, it should almost always be a scatter plot. Or I guess maybe a line graph if you want to call it that. But we're going to plot our data and then add our fit lines. If you have one quantitative and one qualitative, then you're going to have a bar graph most likely, potentially a pie chart. 90% of our graphs this year are going to be scatter plots where we add trend lines or fit lines. There might be the occasional bar graph, but they're going to be very few and very far between. Again, cherry picking data. We're going to critically analyze our data and may occasionally throw out outliers, but we still want to include the important stuff. So we're not going to leave anything out. And then these other ones, bad graphics, that's not something I think we have to worry about, but always make sure we have a title so it's clear what your graph is showing, and if necessary, make sure you add a key. Okay, so some key components to graphs, and ultimately the idea is that our graph should make it easier to understand what we've just found, what we've just collected in terms of data. If the graph doesn't make it easier to understand, if the graph doesn't make it more clear, then it's failed in its purpose, and you need to reevaluate the approach that you took to creating your graph. Data tables are really great. They give detail. Graphs should give a broader picture and should be easier to quickly identify what the relationships are going in. Here's just a graph from XKCD. I'm going to ask you to take a look at it, and based on what we've just mentioned, give me a couple things that may be wrong with it. So what's wrong with this graph? Okay, so let's talk about some of these graphical relationships or really mathematical relationships that we're going to be seeing this year, and how are they going to manifest in graphical form. So the most basic relationship that we'll come across is what we call a direct relationship. When one goes up, the other goes up. One goes down, the other goes down. We call this a linear relationship or a direct relationship. And you maybe recall from math that our equation for a line is y equals mx plus b. And in this equation, y is the y variable, m is the slope, x is the x variable, and b is the y-intercept. Where does our line cross the y-intercept? So this is our general equation for a line, and we are going to use this particular equation probably more than any other this year. This is going to be our most common equation that we keep coming back to, or that we move things into. Now, we have another equation on here, another relationship on here, the proportional relationship. The proportional relationship is a specific linear relationship. It simply is one that passes through the origin. So what that means is that the b value, the y-intercept value, equals 0. And so the general form of that is just y equals mx. Slightly different, subtly different, but they are two different relationships, and we'll kind of see how that comes into play as the year goes on. But for most of our graphical relationships, we're going to want to bring it back to this linear relationship. It gives us a nice clear picture of how the two variables are related. And we're going to do a process called linearization of our data when we have non-linear relationships. So let's look at what that means. So let's start with our next relationship, which is what we call an inverse relationship. An inverse is the opposite, right? It's when one goes up, the other goes down. So in this case, we have period and frequency. As the frequency increases, the period decreases. Now, typically with our inverse relationships, there's no crossing of the or of the x-axis rather, so there's no x-intercept. If we were to carry this out, it goes right. Is that called asymptote, I think? So we're getting closer and closer and closer and closer and closer and closer, but never actually reaching the x-axis. So we have this hyperbolic shape to our graph. Now, if we want to convert that to a linear relationship, we're going to manipulate the data a little bit, and then we're going to regraph it. And so the way we're going to do this is we are going to, and actually let's, the general equation for that inverse relationship is A over X, where A is some constant value. Y is our, obviously, our y-axis variable, and X is our x-axis variable. So what we then have is our general equation for an inverse relationship. What we want to do is try and get this into a form where it's a linear relationship. And if I separate out, let's see here, I have my A, which is a constant. I have my X, which is our X variable. And so what I'm going to do this over here, give myself some room. So we know that y equals A over X. If I rewrite this, y equals A times 1 over X. Now, algebraically, these two things are identical, right? A times 1 over X is equal to A over X. Same thing. We haven't changed anything about the equation. But what you might notice is that now I have a slightly different format for my plot. Y equals mx. All of a sudden now we have it in proportional relationship form. But to graph this, what we see is that our x variable is actually equal to 1 over x. So what that means I need to do is take all of my x variables. Here, x is frequency, so I have 100, 200, 300, 400, and I have to recalculate. So this is actually our old x. Over here, we're going to have our new x. So I'm going to do, this is 1 over 100, 1 over 200, 1 over 300, and 1 over 400. So I have to actually do a little bit of math. I have to calculate what 1 over each of my x variables is. And so 1 divided by 100 is 0.01, 1 divided by 200 is 0.005, so on and so forth. Then, on my new graph, which we have over here, you see that I've now graphed on the x-axis 1 over the frequency. So in the previous graph, it was period versus frequency. In this graph, it's period versus 1 over the frequency. And now what that does is it gives us this really nice straight line that has the equation actually, let's be more specific. So period is t. Our slope is m, whatever the slope of this is. And then my x value is 1 over f. Okay? And so now I've linearized this relationship. It doesn't change anything about the relationship, right? It's still the exact same thing. It's still an inverse relationship. We've simply manipulated the presentation a little bit to give us a better idea of what's going on. And what this means for us, it actually gives us some support that it is actually an inverse relationship. So our first graph, it looked like an inverse relationship, right? It was that kind of downward trending curve. But by regraphing it in this way, if we get a linear relationship by graphing period versus 1 over frequency, and it gives us a linear relationship, that's a strong piece of evidence that it is actually an inverse relationship. So then our next relationship is a square relationship. And when graphed, it should look like this. We have an increasing slope as we start from the lowest point and work our way up. And so it gets steeper and steeper and steeper. We'll get into this type of relationship when we get into acceleration in particular. Again, though, here, if we want to linearize it, if we are going to determine if it is actually a square relationship, we're going to graph y versus x squared. And so again, when we actually, let's come down here. Here's our x, here's our y, and this is x squared. And so obviously this here is 1 times 1, 2 times 2, 3 times 3, 4 times 4. And then over here we have our y variable, which is area, is equal to our slope, which is m, times times length squared times L squared. So this is our x. Okay, so when we graphed area versus length, it gave us our curve. When we graph area versus L squared, it gives us our straight line. And so again, that linear relationship between those two variables is additional support that it is actually a square relationship between those two variables. And then the last one, and these are kind of our most common that we're going to see throughout the year. There'll be a couple others, but this is the majority, is a square root relationship. And in this case, the y variable varies as the square of the x. And our general curve is going to look something like this, where the slope is getting progressively smaller as the x variable increases. And then similarly to our previous relationships, if we're going to linearize it, we're going to start with our x variable. Here's our y. We're going to take the square root of our x. So again, I have to do some calculations. And each one of these here is the square of the actual x variable. And then when we graph that, so here we have period versus the square of the radius, we should get a straight line linear relationship where it's, again, t is equal to the slope times square root of r. So y equals mx. And there's our linear relationship. And as I said, there'll be a couple others as the year goes on, but those are going to be the most common. Make sure you've written down any questions you might have for me next class. Next time I see you, feel free to stop in before then and talk about any parts of this that you may be having issues with. This is going to be something that's important throughout the year. We're going to keep coming back to this. We're going to be graphing constantly, and so it's important that you have a really strong understanding, a really strong foundation of graphing and what those relationships mean. And so if you feel like this is a little bit confusing, please come see me and we'll talk it through, and hopefully you'll understand it better. All right, see you in class.